Hello, this is a Year 12 Maths lesson. We're going to learn what integration is today. Exercise 15a, integrating simple polynomials. It does get harder in due course, but I want you to think of this as really the opposite of differentiation. And so for that reason, I've got a little starter for you, which is all about differentiation. Now, you might remember, for instance, that if I give you y equals 5, x cubed plus 2x squared. Sometimes you're asked to do this thing called dy by dx. This is what the differentiation is. And sometimes you get this word differentiate. Sometimes it'll say find dy by dx, or there's a number of different ways you can say the same thing. But you might recall that you bring the power down to the front and you times. So this will give me 15, but you have to lose the power when you do it. 15x squared. And I've got another term, so I'll do the same with that. 2 to the 4, and that becomes 4x. There you are. That's my answer. So I want you to find dy by dx for these three expressions, please. I'm going to get you to pause the video now, and I'll put up the answers in a bit. So what have I got? I've got dy by dx on this first one is quite simply 2x. And you should remember that if you ever get a number like plus 3, it just disappears. It could have been plus 18, it would still disappear. Dy by dx, and it's just 2x. This one, dy by dx. 2 comes to the front, that gives me 10x minus 2. The x disappears, and the 8 definitely disappears. What about this last one, dy by dx? Well, it's simply 2x. And again, the 1 disappears. It's a minus 1, doesn't matter. Interestingly, two of them are the same answer, and that was quite deliberate. And the reason why it was the same answer is because it highlights the fact that in mathematics, when we do this reverse of this process of differentiation, there's a bit of a question mark as to what the original function was. Sometimes you see we are given dy by dx, and we're asked to find the original y. So, and we're going to think of this reverse process as integration, and integration is the reverse of differentiation, as it says there. So in this case, you see, I know, well, I remember what they were. What was it? It was y equals x squared minus, no, plus 3, I think it was. And interestingly, I had y equals x squared minus 1. Both of these gave me dy by dx was equal to 2x. And so my question here is here, if I've got dy by dx is 2x, what was y originally equal to? And the answer is, well, it could have been y equals x squared plus 3. It could have been y equals x squared minus 1. It could have been, well, I've not even seen it, it could have been y equals x squared plus 100. It could be any of these. And we've got this fact that we've got this number at the end, which it could have been at any number in the world. And so notice what we write. We write y equals x squared plus c. And c is called the constant of integration. And it highlights the fact that there's a number of different things it could have been, and we don't know which it is. The posh name for this is a family of curves, basically highlighting the fact that it could have been this one, any one. Any one of them would still give me dy by dx is 2x. Notice what I'm doing then. I'm trying to find the original function, the original y equals function, if I'm given dy by dx. That's what integration is, as far as we're concerned today. So here's an example. It said dy by dx equals 6x squared. And we want to go backwards. Notice the way this is written. Find the equation of the family of curves. That's a posh way of saying find y equals, which have a gradient function. A gradient function is a posh name for dy by dx. A gradient function given by dy by dx is 6x squared. Now let's just think what happens when we differentiate. So if I get y equals, and I'm going to make up an example here, I'm going to say it's 10x to the power 4. Now my rule says times it, which would be, this is what you do for dy by dx. You times the number, so that's 40, and you knock off a power. Now, if I'm doing the reverse of this, it strikes me as obvious that if I'm going in reverse, I'm not going to well, if I times and add and knock off a power, I think I've got to do everything in the reverse. So I think I've got to add on a power. So that will give me x cubed. It had 6 at the front, did it? Now, when I did this, so the 4 came here, which gave me the 3. Okay, so that you can see quite clearly that 2 has become 3. But I think I've got to divide by that new power. And that gives me 2x cubed. Now I can always check this now. If I were to differentiate 2x cubed, I'd get 3 lots of 2 is 6. And I'd lose a power. Yeah, it's given me what I wanted. Interestingly, it's not quite right. What I should be writing is 2x cubed plus a c, some unknown number which I don't know what it is. What have I written as my answer? Y equals 2x cubed plus c. So there is a rule for integration that I've kind of just gone through. The rule says add 1 to the power, divide by the new power, and don't forget to write the plus c. So you might want to copy all that down, and that's the rule that we're going to be using from now on. Whenever we ask to integrate, we'll add 1 to the power, we divide by the new power, and we'll try not to forget to write the c. So here's another example. It says, find the equation of the family curve as a gradient function. Notice last time it said dy by dx, but dy by dx can also be written as f dash of x if you use function notation. So just be aware these two things are the same thing. The only subtle difference is this time, rather than y equals, when I undo my differentiation now, it will be, say, f of x equals. So I suppose I could write this as if I do y, I'll get dy by dx. But if I do f of x, I'll get f dash of x. That's what happens if you differentiate. And we today are integrating. So when we integrate, we'll start with dy by dx, and it will become y. Or we'll put a different way, if we start with f dash of x, it will become f of x. So just get that in your head. Anyway, the rule's the same. I'm going to add 1 to my power. Now this power here doesn't say it, but it's really a 1. So that's going to go to 3x to the 2. It says divide by the new power. Okay, I'll divide by the new power. And I'm not going to write the c yet. I'll do that at the end, because I've not finished this yet. But this kind of hasn't got any x's at all. So we think of that as x to the 0. And therefore, I can now write minus 1. I'll add 1 to that power. 0 becomes 1. And divide by that new power, which is 1. Now you can quickly see actually a lot of this is superfluous, so it's 3x squared over 2, and all these 1s you don't really need, minus x, and at this stage I'm writing plus a constant. What have I got? 3 over 2x squared minus x plus c. Yes, I've got it right. Here's another one. Find the equation of the family of curves. It's a posh way of writing find x. Well, let's do it then. Y equals add a power. So it becomes 3x cubed. Divide by that new power, 3. Plus 4x, again, think what this power is. It's to the power 1. So that becomes 2. Divide by that new power, 2, plus a constant. And this can be simplified to y equals, look, 3 over 3 disappears. It becomes 1. So that's x cubed. 4 divided by 2 is actually 2. So that's 2x squared plus a constant. And that's that. Notation, look, this is the posh notation. We've already seen this method where you get written dy by dx equals 2x, and that will let you find y. This sometimes is written in its own right. Rather than dressing it up as being dy by dx and find y, they'll just say integrate 2x with respect to x. That's the way you say it. And the rule is the same. I'm going to add a power. So they add a power to this. This becomes 2x to the 2, because this is really to the 1, and divide by the 2. Notice the 2's cancel, and I'll end up with x squared plus c. So this is a new notation. This means integrate. So another way of writing this is to, as it says, this is called the integral sign. The dx is a bit weird, but we have to get used to saying it, because later on it won't always be x's. and you read it, so you say with respect to x. So here's a new question. It says, now look, again, this means integrate. So this is what I'm trying to get you to do, really, just learn this notation. This means integrate 3 with respect to x. Well, this just becomes add a power. There's no number, so it just becomes 3x. Don't forget your constant. Oh, it's a bit naughty. This was integrate 3 with respect to t. So because that was x, I gained an x. Because this says t, I've got to gain a t. So it becomes 3t plus a constant. Well, that t's are actually more common than you think. T stands for time, I suppose. And look out for dodgy powers. Like x to the minus 3. I'm not sure what you like. I've got to add a power to minus 3. This becomes minus 2. Who was thinking minus 2, or who was thinking minus 4? Be careful with negative numbers. So minus 2, and then I divide by that power. Then it becomes minus 3x. So it says minus 2 now. I've got to add a power, so it becomes minus 1 divided by minus 1 plus a constant. And this actually simplifies to minus a half, I suppose, x to the minus 2 plus minus divided by minus plus 3x to the minus 1 plus c. Now this can actually be tidied up even more. I'm not sure if I've done it. No, I've left it like that. But it can be tidied up a little bit more. Now look, here's a little thing I'm going to get you to do. All I want you to do is to write down what happens when you add 1 to these numbers. It's not as obvious as you think. So I'm going to pause the video now. I'm going to ask you to write in there, look, to this one. Minus 2, if I add 1 to it, I get minus 1. That's all I want you to do. Go through those, please. I'll pause the video now. I don't know if you've done that or not. I'm just going to add 1 to these. So they'll add half to 1 to a half, you get 3 over 2. Or you could have written 1.5 or something like that. But 3 over 2 is the posh way of writing it. It's much better, actually, as a fraction. So if you did them on your calculator and cheated, you would have got these. Your calculator would have said, oh, I prefer writing it as top-heavy fractions. So this is all I'm doing. I'm adding 1 to it. Adding 1 to it. This one becomes a half. This one becomes 3/4. This one becomes 1/4. This becomes 2/3. This becomes minus 4. This one's a bit weird. It becomes 0. Have a think about why you think that might be weird. But nevertheless, here's another example with these dodgy powers. Now notice it's in t's, so my answer is going to be in t's. Integrate 6t to the half. Now remember the rule, it says add a power to a half. Now if you add a power to a half, you get 1 1/2, which is best written as 3 over 2. But then I have to divide by that 3 over 2. Minus 10t. Now minus 2/3, add 1 to that, you actually get a third. And again, don't be shy on your calculator. Type in minus 2/3, add 1. See what comes up here. It'll come up as a third. Well, in which case either get good at it, or just learn to do it in your calculator. Now, we've got to tidy this up. Now you can do that in your head or on your calculator, I don't mind. I get 4t to that. I reckon this is minus 30t to the third. Don't forget your c. Yes, good, I've got the right answer. Look, and I've got through all the questions on this exercise, and I just want you to have a look at those. This is exercise 15a. We'll finish these in class in terms of the questions from the textbook. And notice we're back into the year 12 textbook now on integration. I know, relatively recently we've been doing some year 13 work, so best of luck.